Okay, then let us just continue. We are continuing with the PowerPoint from last week. Yes, this one is not the intrusion. No, just check this one, the intrusion. Yeah, go through that we had already. Yes, we are continuing now with down a little bit, down. We are continuing today up with this one. So now today we are continuing with the crystallization or the formation of these layered intrusions, which are an important ore deposit, yeah? So, and I mean, if you have such a melt which is cooling down, then you are crystallizing some minerals, and the others will sink down, and the others will float up, and the others will be in the middle zone. So in these minerals, it does not matter what type of mineral it is, they are growing and then they are becoming a zonation. And if you are getting more and more minerals, then your melt becomes less and less mobile, yeah? So and then it becomes stacked. So if this melt becomes then cooled down very fast, then you have still a lot of, then you have actually a glass, yeah? And within this glass you have then some other mineral inclusion. And I mean a typical rocky glass, that is for example here the obsidian. Okay, you have a fine-grained matrix with some bigger minerals inside. So and if you have less minerals inside, then we are talking about accumulates, a little bit more than we have mesocumulates. And if you have a high concentration of crystals in your melt, then your melt getting less and less mobile, as I told you just right now. So again, we have then what we are talking then about the autocumulus or autocumulus growth. So here we have at the top the accumulus growth, the mesocumulus growth, and the autocumulus growth. Yeah. So and if we have here the flow velocity, then the flow velocity from the autocumulus is slower, as I told you, mesocumulus rate is a little bit higher, and the cumulus is then flowing much faster. So that is now this relationship. Next slide. So if you have then a flow rate, and the flow rate or the thing becomes then rigid at one time, then it will stop, and then you have a layer. And here we have one layer, here we have the next layer, and here we are producing the next layer. So in such a layered intrusion, as I told you, you can only produce in mafic wells, yeah, because there you have at the beginning you have a lower velocity, then you have a higher flow rate, and while you are crystallize a certain type of minerals, yeah, then your well becomes always, or the flow rate of your melt will always decrease till it becomes stuck, yeah? So in that is like I told you this example from the traffic jam, yeah? If you just have too much cars on the road, then the traffic becomes slower, yeah? And that is according to Peter's law, yeah? So, but if you have produced from the beginning at the same rate minerals, then the flow rate will just continue, yeah? So you have then always to produce more and more minerals of one or two species. They will grow, and then it becomes stacked. So if we are looking, for example, here for the andesite is an intermediate rock, then you have here also some minerals in a very fine-grained matrix, yeah. But this melt had still a very, very high flow rate. If you are looking, for example, I just saw it yesterday somewhere. Andesite, for example, this andesite has the lower flow rate because the other antigolds inside, they are bigger, yeah? So if you have then at one time, at a certain time, so many, if you have formed at one time so many crystals, then that you can make a reheat layer, then it will become stuck. Yeah? So if we are talking about the granitic melt, then the granite has much higher SiO2 inside, that means silica, and I showed you just last week. Then you have the connection between all these silica tetrahedrons. Then you have the connection between all these silica tetrahedrons, and therefore you have the connection over the oxygen bonds or over the oxygen bridges from all tetrahedrons to each other. So therefore a silicate melt has from the beginning a much higher viscosity. So and here the single crystals here, they are not conducted, which is connected which is each other over oxygen bridges. Yeah, it becomes then just stuck because you have too many of the single minerals. Yeah. So I mean, if you are watching the traffic flow, if you have the high traffic flow, as I just mentioned to you, then the single cars and buses, they are not physically connected to each other. Yeah, I mean, there you can then also make a rigid crust if you have a crash. Yeah, so then they are connected. It becomes just stuck because the traffic is too high. Yeah, and then it's okay. The same case for the layer intrusion. Yeah. I hope that is clear. There is also a question in the test, I think test 2, how this is with the viscosity, yeah? And with the tetrahedral coordinated cartons and octahedral, yeah? There is a question inside. And I'm not saying this for nothing, that you should check this exactly, because maybe such questions you have to answer very soon as well. Showing where is the thing of layering. So then I showed you last week some pictures from my own research with the fluid flow, yeah? That you can have an interconnected fluid flow. So if you like to know this later on, because you are working for an exploration company or something like this, yeah, and then you are, of course, you are taking your rock samples, then you are making your thin sections, and then you are watching them under the microscope. Unfortunately, we do not have here a microscope in class, yeah, so then you have to do this in a self-study. And then you can just watch this triple junctions between the grain boundaries, yeah, and then you can measure very easily what's the angle between, yeah. I mean, you can just make it with your naked eye under the microscope, yeah. So, and if the angle is smaller than 45 degrees, yeah, I mean this angle here, yeah, that is at 0, then it allows that you have an interconnected network, and then you can have a fluid flow through the grain boundaries, yeah. So I mean, we are talking always here in class about fluids and volatiles, yeah, and how they are related in the formation of ore deposits. And you know by now that is one of the most important things, yeah. So, but if you are not dealing with very hot stuff, like in the Earth's metal, that everything is ductile, yeah. So in the Earth's metal, you have the movement of grain boundaries, yeah. There we can show them a movie. In the Earth's mantle, you have the movement of grain boundaries because everything is ductile, because under this high temperature and high pressures, yeah. And I will just check at the end of the class if I can find in the, on the internet a dislocation creep. Yeah, that is how it is called. That is the dislocation creep. And that is then just the movement of the grain boundaries through a rock sample, yeah? I mean, we don't know how ductile this stuff is and how it looks like there, you know, is it like bubble gum or I have no clue. But anyway, when you are sampling your rock sample, yeah, then you cannot watch anymore, the dislocation creep, yeah, because you are getting your rock sample in a frozen stage, yeah. So, but if you can observe these triple junctions between the grain boundaries with an angle between lower than 45 degrees, then an internet network was possible, which allows you to have fluid flow through your rock sample. So if you remember from my talk last week, I showed you also the synchrotron measurements, yeah. I have there a couple of publications about this stuff. And if you are detecting totally embedded cracks, yeah, where the fluid, the remnants of the fluid could not disappear, these are then such remnants of the dislocation creep. So, and that we are calling nowadays cracks, yeah? So, in these cracks, or dislocation creep, plays a very important thing in the industry. So, because the dislocation creep, or this formation of crack propagation, yes, the crack propagation, that is something very important. Because if you are starting with a small crack and this got under stress, it will just run through. You know, it will just run through the kimberlite, as I told you, yeah? It goes then up from a depth of 200 kilometers to the Earth's surface within 10 minutes or something like this, yeah? Or it goes up like the crack, in a glacier, yeah? There you have also fluid inside, and then it propagates just through, yeah? So, but we have two very famous accidents in the past which dealt about such cracks. So that is the not nonsense what I'm talking here about, and it has really a very, very application, very important application. So the first big accident that was in 1912, what was this? 1912. That was Titanic, yeah? So in Titanic, that was Titanic. So and Titanic died actually, or the people died inside the ship had just sunk. It sunk because it was made by the British, and it sunk because the British used bad steel. So, and this bad steel contained too much sulfur. Yeah, I mean the version is, Titanic crashed in an iceberg. Yeah. So, but I mean this iceberg, which was just looking out of the surface so much, cannot produce a hole of a length of 63 meters. 63 meters, yeah? I mean, if this was the ship here, so, that looks then like this, yeah? Just the bottom, then the crack was on the side, 1/3 of the ship through. So, and I mean to have such a huge hole, is it, yeah? Then you need something more as an iceberg. But the iceberg was the trigger. But if the British would have used German steel and not British steel, then it would be maybe still around. Because, I mean, all these ships, you can also see it on the ferries, yeah? They are not made up of one piece, they are made up of plates. Yeah? And then nowadays they are welding all these plates, yeah, with each other, yeah. But in former days, if this is such a plate, yeah, and then we have an overlapping zone between these two plates, and then they have put holes inside. So in there they put bolts inside, yeah? Bolts, yeah? So in these bolts they were just, before they put it inside, they looked like this, yeah? Then they are putting inside and then they were hammering the bolts together, yeah? So because the steel was too cheap, if you have then here such a plate, the steel was too cheap, yeah, or in this case there was too much sulfur inside. So and then you have here the hole, yeah. So and when they put the bolts inside and hammer it, then you have here everywhere around these micro cracks, yeah. So and that was then a very weak zone. So and when the ship rammed against the iceberg, then I mean the bolts went out from all the plates. Yes, and that causes then that you have this huge hole over a length of 63 meters. It was then, you know, just like if you are playing domino, you know domino, you are just kicking one stone and then they are clubbing through, yeah. So that was this, that is actually the famous thing. And then another thing was 2003. What happened in 2003? In 2003, Columbia crashed down. You know, the space shuttle, yeah? Columbia was out 1 of 5. Yeah, there was the Discovery, the Columbia, the Endeavour, the Atlantis. And what was the first one? I think there were all of them. Did I mention 5 or 4? 4. Which one crashed down at first? I think this one I have forgotten. It does not matter. But the reason why Columbia crashed them down, that was also crack propagation, yeah? So if you are looking at the nose of the space shuttle, yeah, then you can see there are a lot of tilts, yeah, they are of this size, tilts, like on an oval, yeah. So and between these tilts you are using a special cement, yeah, to put the tilts together, and this cement has to be used that no air is coming in, because as soon as the space shuttle comes into the Earth's atmosphere, then the nose becomes very, very hot, yeah? So there were between these tilts micro cracks, and then the air could go through, and then the whole space shuttle was just burned away, yeah? So and there you have this formation of cracks and crack propagation, and that is something very important. Not only when you are studying rocks, they have in the industry a lot of problems with this, yeah? So in there I gave you just 2 examples, and now we are continuing here with this stuff with the next slide. So, then here that is written wrong, yeah? If you can just remove this in your documents, and make it the other way around, because these are the autocumulates, these are the mesocumulates, and these are the accumulates, yeah? Because here you have much more melt inside and some crystals. Here you have some melt pockets inside. And here you cannot find any more melt pockets, and you have very nice triple junctions. And that is then just when your whole stuff becomes then rigid. So that means this belt is has a higher flow velocity, is more mobile. This is intermediate, and then this one is rigid. But that we had already before. Yep. So, and if you are working on such a layered intrusion, then you would like to get some information where you can expect in which depth, because such layered intrusions can be very, very thick, yeah? And we will continue just on in our next 303 class with the continental flat basalts, yeah? Such a layered intrusion is a continental flat basalt, so they can be up to 70 meters. They can have a thickness of 70 meters like the Chongqing Laccolite or the Tasmanian Diabetes has a total depth of 460 meters. Or you have here in Kilauea, we have a total depth of 100 meters. So, and I mean, certain ore minerals are also always associated with certain indicator minerals, yeah. And I mean, the ores itself, they occur in a much lower concentration. So, and I mean, if you have this diagram, yeah, I think this one they have made up. They just use drill cores, yeah. That is the easiest way, yeah. Or you are sampling rocks. That is another way. I mean, if there is no vegetation at this place where the layer intrusion is, again it depends how many is at the Earth's surface. Then you can just walk on it, and then you are taking samples from everywhere. Yeah? So, and then if you are looking, for example, for a chromium ore deposit, yeah? For a chromium ore deposit, where do you think is the best place here for looking at it in detail? That is here where we have most mafics. Yeah, because I mean, chromium is always related to very mafic rocks, yeah, because very mafic rocks, they crystallize at very high temperatures, yeah, and the chromium or the mineral chromite is then located actually at the bottom of the magma chamber. But if we have such a situation like I showed you before, that you are building certain layers, yeah, then I mean this chromite is concentrated there, or can be concentrated there, where you have it for just a rigid crust, yeah. Or it can also be that you have an influx of a second or third weld batch. Yeah, you never know this. So that is then always where you have the highest concentration of mafic rocks. And there you are going and looking for. So then we are having the Tasmanian diabase. If you are looking here for a chromite ore deposit, in which depth you would look? At the depth where you have the highest or the lowest density? Which has a higher density, a mafic rock or a granitic rock? The mafic, yeah. So then you will look somewhere here, yeah. So and then we have here the Kilauea. You know Kilauea, that is now, for those who are coming to the ES303 as well, we talked just yesterday about the Kilauea. That is now the most recent and active volcano of the Hawaiian hotspot. So, and if you would look like, therefore, I'm saying always chromium, I can also say vanadium or platinum or all this very high grade stuff, yeah, or titanium, yeah. So in which depth you would here start? I mean, you are looking therefore for a rock having a high magnesium concentration or low magnesium concentration. High or low? High. Yes, because mafic rocks which crystallized or formed at high temperatures, they are automatically more rich in magnesium. Yeah. So that is the way how to do it. Yeah. For example, if you are going here to the harbor, then you can see from time to time these drilling ships, and they are drilling and they are around in the ocean floor because there they are expecting the high valuable platinum group elements, and then they are drilling everywhere in the ocean floor. So and then you can immediately say to them in which layer they have to check it, yeah? That is exactly this game, yeah? So next slide. Yeah, here we have the boat in percent, yeah? And here we have the height in layer. So why do you think you have at the bottom of the layer more olivine and less plagioclase, and the pyroxene you have here a higher concentration? Why is this? That is because, I mean, such a layered intrusion is actually a magma chamber, where a crystallized magma chamber where you can walk above. Yeah, I mean, like for those students who will visit sometimes Skoro, yeah. I mean, there you are also, when you are walking along the beach, you are just walking over the whole magma chamber. So, and I mean, at the bottom of the magma chamber, you have, of course, more olivine, because the olivine has a higher density and it is just sitting down here. So, whereas the plagioclase has a lower density and it's floating up, and therefore it is sitting at the top, yeah? So, and the pyroxenes, they have also a high density, but if it is, for example, an autopyroxene, then they are somewhere between, and then they are just swimming somewhere in the soup, yeah? So, but now we have the distribution of the grain size, and that is just how long they are growing, you know? And it has something to do with the growing rate. So what important is actually this contribution, because that shows you how the minerals are distributed in the magma chamber and how this is related to the sinking of certain minerals and the other one floating up. So next. So now we have here 3 different types of magma chambers. There's also a question in the test. So we have the classical magma chamber, yeah, where you have here at the outermost zone, you have the olivines, yeah, or more olivine-rich rock. Then you have here, you have then also the pyroxenes. And here in the middle you have then your more granitic or felsic rocks. Yeah, that is just a classical fractionation, and we have done this by now a lot of times. Yeah. So and that is how the classical magma chamber is. So now we have the second one, there you have a solidification front in the chamber, yeah? And these solidification fronts, they are produced within these 3D layers, yeah? So that means when you are producing certain minerals and they are getting somewhere that's stuck, yeah? Then you have here the formation of different layers inside, yeah? So that means in such a case we are then not forming we are not forming from our basaltic or mafic belt a felsic belt like in the classical magma chamber, yeah? In this case, number 2, we are forming such a thing like a layered intrusion, yeah? You are forming always at certain levels, you have the solidification fronts, yeah? So in number 3, we have the solidification front chamber that is here, yeah? But you have also the fractionation and crystallization and differentiation of certain minerals, and they are sinking then here to the ground, but also going here to the side and floating up, yeah? So, and when we are discussing this about the cooling rate, which magma chamber you think have cooled slowly and which has cooled faster? I mean, if we are forming from a mafic belt and granitic belt, as in a classical magma chamber, then the cooling rate is probably what? Fast or slow? No, it's slow. It's very, very slow, because then you cannot have all this differentiation, fractionation, and assimilation, and contamination processes to form from your originally mafic belt a felsic belt, yeah? That can quite take a couple of million years. So, and here we have now this solidification front here, like you can see in the layered intrusion, and there we have the fact that it has cooled down comparatively faster, because otherwise it has also cooled down slow, yeah, but not that slow like this one. So, and here we have the situation that you have at first fractionation and differentiation, stuff is sinking down, floating up, and then you have such solidification fronts, and that is then just a medium rate, yeah? So, and here in the classical chamber, you can then see you are starting here with olivine and dioxide, and then you are going down here, and that here stands for silica liquid, yeah? So, and then it becomes always, here in a classical way, it goes from mafic to more silica rich, yeah? So, but here you are form all this mineral at the same point, yeah? So, and then you have a faster cooling rate, yeah? Because it becomes then stuck here everywhere. I mean, here you have some small spots maybe where you have still produced some liquid silica. So, in this case, we are forming these parts also very fast. We are sitting here, yeah, with CPX and olivine. Here we are getting then something very magnesium rich. Here even more magnesium rich. Yeah, here we have at least a little bit calcium inside. Yeah. So and here in some spots we have then also silica liquid rich pools left. Yeah. So but in the classical way we have just one cooling rate, and it becomes then always more and more silica rich due to differentiation and fractionation processes. Yeah? So in the other two cases, there was something distorted. Yeah? So and that can be the cooling rate, yeah? Or there was an influx from another melt, yeah, could also be such things. Yeah? So next slide. This we don't need. Yes, that is also very thing. The cooling rate, yeah, because we are now at T-Unterkühlung, that is German. T stands for temperature, and Unterkühlung, that is just the cooling rate. So in that here, that is the crystallization rate, and that's the rate how you form the nucleides. Yeah, I mean if you like to form a crystal out of a melt, then you need that first a nucleid. Yeah, I mean you need a trigger. Yeah, so in there the crystal is then growing. Yeah. So at the beginning, you have the formation of very fine-grained accumulate, yeah, very fine-grained accumulate, and you have form a lot of them, yeah. And number two, you have then formed from accumulate at the beginning. You have only a few crystals in the melt, and they are small, yeah? So, but while you are cooling down your melt, your crystals will grow, yeah? So, and then you also increase the number of your crystals, yeah? And then you will form here an autocumulus, and that means your melt becomes more and more less mobile, yeah? Yeah, just write it down also with the English, yeah? That is the fine-grained accumulus, and that is the autocumulus, that is the cooling rate, that is the crystallization rate, that is the rate of the formation of the nucleides. Have you written this down? Yes. This number one, that is fine-grained accumulate or accumulus. Fine-grained accumulus. Then number two, that is the autocumulus. So the number three, we have the coarse-grained autocumulus and stratiform pegmatoids. So in number four, you have volcanic textures. So and if we are talking about volcanic textures, then we are talking about very fine-grained stuff, which cool them down very, very fast. Yeah? So and then you are making here at the top 1, 2, 3, 4, 5. That is in English the same like in German. So you don't need a dictionary for this. So again, we have written here that here delta T, that is the cooling rate, that is the crystallization rate, that is the rate of the formation of the nucleides. So now you have this. So at the beginning we have a high crystallization rate, and there we have the formation of fine-grained accumulates, yeah? So at number 2 we are producing then autocumulates, because our fine-grained accumulate becoming always more and more, the crystals are growing, and then the melt becomes then more and more less mobile. So and here at number 3, we have then the very coarse-grained autocumulates, yeah, and some pegmatoids, yeah. So and then we are cooling down very, very fast. Then we have here at number 4, we are starting to have volcanic textures, and that is then actually like volcanic glass, which I have given around. Now I become stuck here, or it's already back, I don't know. So and then we have the formation of the nucleid. We are having at the beginning less and less, and then we are increasing and increasing till 4. So and here, while we are cooling down fast, we are forming then glass, yeah? So and therefore we do not form any nucleids, because the cooling rate is too fast. So I hope that is clear. Yes, not nucleids. The nucleids. So these are the nucleids. So we have the next slide, please. Yes, that shows you the movement of the magma composition with crystallization of the autopyroxene and the plagioclase. So we have a starting composition here of a silicate magma, which we have in our magma chamber 99% of silicates. So and these silicates are here in a gabbroid melt. That means we have a basic to intermediate melt, yeah? Such a gabro can have less than 50% silica or a little bit more. So again we have 0.3% oxides, sulfides inside, and 0.7% oxide. So actually for the formation of titanium or magnetite, you know, for iron, yeah, we need then oxide, yeah. So, but now when we are watching our starting composition, we cannot produce very much sulfides from this sulfide-bearing minerals, yeah, and also not much oxide-bearing minerals, because there's not that much inside. So therefore, it shows you also that these minerals which are the ore minerals in your former silicate-rich belt, occur only in a minor concentration, yeah? So, and then you have this starting composition, and then we are following this arrow till here, and then you have it. At this point, you are going here and then there. And you know that then you can see that the concentration of your sulfides and oxides is actually very, very low. And they become enriched then in a later magmatic stage. Yeah? Not in the pegmatitic stage, but also not in an early magmatic stage, because when we are starting here to crystallize, then our other minerals inside, yeah, it depends if it's an olivine gabbro or intermediate gabbro, then you can have even a little bit quartz inside. Yeah, we have here the crystallization, yeah, of orthopyroxene and plagioclase. That happens then at first, and in the later stage you are not having then the formation of the sulfide and the oxide bearing minerals. So in the liquid and the liquids passes, that is this one, and that is within a falling temperature between 1200 to 800 degrees Celsius, and 800 degrees Celsius, that is then at this temperature where you are then for your sulfide centers and some other oxide minerals. Yep. That we don't need. We don't need. We don't need. No, we don't need. Okay, so that was so far to the layered intrusions. And you have the PowerPoint on Google. And you have also the description of all this stuff also on Google, yeah? So now we are looking for the movie about dealing with the dislocation creep. Or are you connected here to the internet? Okay. Then I can save money here. So then you are just putting in dislocation creep. Dislocation creep. Dislocation creep, that is written in such a way. This with an S. This L. Dislocation. Dislocation creep. C-R-E-E-P. Yep. Then we have here, we have found it, yeah. So then there were some movies that we go down, go down, go down. This is good, I think that we had, yeah. So this is just, I don't know what for material it is, but there you can see this is how the grain boundaries are moving through. So, and I mean, if you are sampling the rocks and you are observing all these grain boundaries, that is then in the frozen stage, yeah? So I mean at first you have only melt, then of course you have the crystallization, but the whole thing is still very ductile. So they are just moving through, and there I think they have used aluminium. So yeah, here the dislocation light. That is now at 100 degrees Celsius, yeah. So that is now, I think it's some metal, yeah. But here you can also see all the different oxides inside. Here as well, yeah. So and that is just how things look like that in nature. But I think that is now not that what I expected. If you can just go back. Yes. Can you see it? They are just running through. Yeah, it looks like acid and military, yeah. Yeah, maybe we can also watch this one, yeah. No, that one we had already. If you are just going back, no back. Yes, this one. No, that was this one. Yeah, maybe we can also watch this one. Yeah, they are moving nicely. So yeah, I think that is enough for the movies. You have seen it now, how this looks like, and there is in the rock exactly the same, yeah. So and if you are sampling your rock, then this is just the frozen stage, then, yeah. So then I have to make some announcements. We are still busy with the marking process, because some of you are sending me today an email about the marks, yeah. But I got the field books just after the field trip, and he has already all the attendance and made also some marks how you are doing in the practical. And then I will combine this with the test 1 marks, and then it is there next week sometimes, yeah. So, but everybody passed the test 1, so don't worry, yeah. In both classes, yeah. So then I will see the ES303 people tomorrow here for a class, because there we are short of time, yeah. Because we lost some classes, yeah. So when the ES301 people are going then with Satan to the lower campus, and then you can continue with your swimming pools, yeah? Yeah. So that you can finish the models until the end of the semester. So again, the classes will last till the end of the semester, as I told you, because we have done the field trip before. So next week in the ES301, we are doing then, we are repeating the geothermal, yeah, because there I have some pictures to show that it's not too much. And then we are doing, the P waves and the S wave anomalies, you know, for the geophysical part, yeah. So then I can do it with another hour. And the week after that, we will show you 2 movies, yeah. One movie is about eruption from Mount St. Helens, yeah. And the other movie that is mountain tsunami from 1953 in Italy, yeah. So because there you can see how this tsunami was created, yeah, which killed a lot of people by a landslide, yeah. So and then we are done with this class. And for the ES303, I will then do tomorrow the announcement what is missing and what we have still to do. And for the remaining 2 weeks in the practical, you can just continue down at the lower campus with your experiments. Yeah? And then you can think about if we should have again such a session to run the experiments or not. Yeah? Okay, then see you tomorrow. Yeah? So then let us meet all tomorrow here, and then ES303 people staying here, and the other ones going with them down. Yeah? What? Yeah, those who are doing ES303 should stay. And those who are doing only the ES301, they are going down with them. Because we have to do some additional things in ES303.